Okay, so I'm really happy to introduce to you Dan Klein from Berkeley. Dan is somebody who just graduated from Stanford this year in 2004 to the tune of job offers from like 9 universities and all the best corporations as well, and ended up at Berkeley. He's won, I think, 3 Best Paper Awards in the past 2 years for A-star parsing, unlexicalized parsing, and maximum margin parsing. And he's going to be talking today not about parsing, but about grammar induction, where he currently has, I think, the best results in the world. He's also worked on a number of other machine learning problems, including, I guess, word sense disambiguation and named entity and part-of-speech tagging. Is that right?
Something like that.
Something like that. Anyway, he also has the virtue of being an exceptionally clear speaker, with nice, clear slides with big enough fonts and pretty pictures. So I'm looking forward to his talk, and if you like his talk, there will be more of him tomorrow. He'll be here from sometime before lunch until about 3:30 when he leaves for the airport. So.
Thanks. As Jason said, I'm going to be talking about parsing. I'm going to be talking about unsupervised learning of grammar in this case. And I should tell you there are 2 things I should warn you about these slides. One, there's about this much that you guys don't get to see, so apologies in advance. Second, I very rapidly adapted these from a Stanford template. So if anything says Stanford, pretend it says Berkeley. Okay. So I know this is a mixed audience, and forgive me if some of these introductory slides are general or controversial, but big overview, as far as I can see it, for natural language processing is this is what we're aiming for. So if you watch the movies, you get robots that talk to each other and that talk to us and translate for us and refuse to open the bay doors or whatever it is we want our robots to do, and everything works nice and smoothly. Interestingly, the one thing they don't do in the future well is speech synthesis, which is probably the only task in NLP we can solve today. But this is the reality. Just yesterday in the hotel, I saw a commercial basically promoting a phone because it had more buttons over some other phone that did speech recognition badly. So today, it is actually a big deal that if I want to enter information into my phone, I have to press a button over and over again until I get the letter I want. And this is a far shot from C3PO. This could lead us to ask the following questions. Why is this endeavor so hard? If you believe Star Wars, an 8-year-old can build C3PO, but we can't really do much of anything today. And the second question, what exactly do we need to do in order to make all of this happen? So the first question has an easier answer. Why is this so hard? And I'm going to give an example, and I'm sure a lot of you are already convinced of this. I'll give you an example from syntax. And the example is I think about all the different kinds of noun phrases you can have in English. And I think, how complex could this possibly be? I can start enumerating them. I could just have a plural noun like cats. I could have a determiner like a cat. I could have a determiner and an adjective and a noun, an angry cat. I can have a cat in a sink. I can have a cat and a dog where I've conjoined 2 nouns. I think, how hard is this? I write down all of the different realizations of a noun phrase, and I encode them in some kind of finite state automaton. Here's a finite state automaton with 8 states or so, and I think I'll do this until I run out of options, right? And I have my whole grammar written down. Now, the problem is if I go to a collection of hand-parsed sentences like the Penn tree bank that I'll talk more about later, you get a finite state automaton that looks like this. And it's not really any easier to see if you get the other 20 pixels, right? And so you say, I can't see that, and I zoom in, and it looks something like this. And you say, I can't really see that either, so you zoom in again. And finally, at this kind of magnification, you can start to see individual rewrite rules. This thing is immense. There are so many different ways you can realize a noun phrase that to try to brainstorm all of them is quite difficult. So here's 2 answers to why it's hard. One, it's very hard to serialize out our knowledge about language. And secondly, if you have big finite state machines like this, you have memory problems, you have efficiency problems, you have sparsity problems if you're trying to estimate statistical models. So I could repeat this argument for things other than syntax, but I'm going to move on to the big picture of why we don't have NLP. Now, this is a slide that may or may not be controversial, and if you're all actually NLP people, you already know this history. This is the kind of highly cleaned history of natural language natural language processing. That is, since about the 50s, people wrote rule-based systems. Just like in AI, writing down declarative knowledge, it turns out, and then you feed these things into some kind of theorem prover or something like that. And this didn't work well for the reasons we're told. The systems that result are very brittle, and experts are expensive. Especially, what you need here is not only experts, not only people who understand language. You need people who understand how they understand language, and those experts are even harder to find. Okay, so something magical happens in 1985. I'm not entirely sure. I was 8. But something magical happened, and we move into this new era where there are statistical models. And what statistical models do is you have a bunch of examples of the correct behavior. And you do some kind of statistical learning to relate the input with the outputs that you want, and then you learn how to reproduce those outputs somewhere else. And this is great for lots of reasons that we all know. You get robust evidence combination. But broadly speaking, and this is the controversial part, I would say this still basically hasn't worked. Most tasks that you'd really like to do with natural language processing, we can't do yet. And there are a lot of reasons for that. Partially that the problem's just very hard. But one reason in particular is we've banked all of our methods so far on systems that require input examples of what the correct behavior is, and there's just never enough data to do that. I'll say a little bit more about that in a minute. The framework we're in is what's known as supervised learning. I'm sure most of you are familiar with. I like to think of supervised learning as something like this. You have a bunch of, you have systems which learn to duplicate correct analyses from training data. And I've already talked a little bit about why it's hard, but the main thing I'd like to point out is the thing that's hard is not only learning a good hypothesis from your training data. It's hard to get your training data in the first place. So over here, bonus points for anybody who knows what this is actually a picture of. But over here, you might think that this is supposed to represent the systems being instructed how to parse natural language. Actually, this is probably a better example of what it looks like to create a data set. Of course, the people at Penn had computers instead, but you sit a bunch of people down and you have them do something very boring for a very long time. These data sets are hard to adapt for new purposes. There's always new languages, new tasks, and data sets are expensive. And the problem with this is we suffer from something I like to think of as corpus addiction or data set addiction. We don't work on the interesting problems. We do whatever we can with the interesting data sets. Everything revolves around data sets. Okay, so here's an example. The Penn Tree Bank, I've mentioned it. I'm sure a lot of you have worked with it. And this is about 50,000 sentences that was hand parsed. It took several annotator years, and it probably looked a lot like this. Let's contrast this with what I'm going to argue for, which is the other extreme. And of course, the reality of what's going to work is probably in between. I'm going to argue that what can be made to work is unsupervised learning, which I think of as something like this. A larger group would laugh louder. The basic idea is you don't give examples of the correct behavior. You just give examples of the data, and the system, through some process, detects patterns. Now, of course, this is a good idea provided it works because you always have data. If you want to test a system, if you want to use it for anything, you've at least got your test data. So you've always got the right data. And looking into this could teach us something about how machine learning and clustering works. And there's even reason to think that this might be possible for language in particular, because we've got one working prototype of a language processing system, and it seems to more or less work in an unsupervised fashion. So that's some good argumentation. We're going to work purely in this talk. What I'm going to talk about in specific is starting with text and trying to detect some kind of grammar over that text. This is a very small piece of what it is to know a language, and we're not going to have any notion of what the sentences mean, what the sentences are going to be used for. There's no dialogue. There's just going to be sentences come in, some guess at grammar comes out, and of course the guess can be wrong. Okay, so here's the outline of the rest of this talk. I've so far tried to motivate why it would be great if we could make unsupervised learning work for natural language processing. I'm going to present two kinds of syntax. So I talked about learning grammar. People mean a lot of different things when they talk about grammar. I'm going to present two kinds of syntactic structure and models that are designed to learn those structures. And I'm going to talk very rapidly on how to combine them. Mainly, I'm just going to tell you what happens when you combine them. And I'll make some conclusions. Okay, so for the rest of this talk, I'm going to be specifically focused on syntactic parsing. And parsing, broadly taken, assigns some kind of structure to a sentence that encapsulates grammatical relations. So one thing I might do is put up what's called a dependency structure like this. I have Shaw Publishing acquired 30% of American City in March, and I've indicated with arrows facts like in March, is linked into the acquisition. That's when the acquisition occurred, and so on. Right? This is one kind of syntactic structure that says how pairs of words relate to each other in terms of their syntactic function. Why is this useful? This is useful because these attachments can help us answer questions like, well, this is some kind of acquisition event. We know that if we see the word acquired, but who did the acquisition? Well, Shaw Publishing. When was it acquired? In March. What was acquired? And so on. So the hope is that we can find lots of uses for this kind of syntax, and this is an example of what that might look like. So what we're going to try to do here is start with raw text, off the web or otherwise. I'll talk a little bit later about the input data I'm using, and we're going to start guessing structures according to some pattern detection mechanism of some kind, and we're going to see how we can arrive at good structures, where I also have to define for you what good structures are. Now, some people have argued that this should just be impossible, right? This idea that you start with text and then you identify the syntax. Most famously, one of these, depending on who you consider famous, the math people or the linguistics people. But one of these you may have heard of. There's the Gold theory about non-identifiability of the limit, and Chomsky's made arguments based on the poverty of the stimulus in child language learning. I call this the give up before you try approach. Here you have lots of people historically who have thought that this should basically be possible because you look at the data and you think, okay, it's just obvious there's a noun phrase there, how hard can this be? And lots of people have tried lots of things. This is a partial list. This is a very partial list. This is only the systems that I'll have time to tell you about today. Okay, so here's a bunch of attempts, and there's lots more. It basically still doesn't work. This is the give up after you try approach. And usually attempts have fallen into one of these two categories. What I'm going to try to argue to you today is that we can make unsupervised parsing work reasonably well. Reasonably is in the wrong place. So I mean reasonably to be here. There's a reasonable notion of well. I should say right off, these systems are not, and probably in the near future will not be as good as a supervised system. Right? You can always do better if you know what the answer is. All right, so let's back off a little bit and imagine this is a concrete task that I present to you, because it's your job to do some kind of grammar induction. I stick you in a room with a computer and a whole bunch of text, and I give you the general idea that you're trying to link up pairs of words. So you think about the following. Congress narrowly passed the amended bill. Well, Congress passes things, bills get passed a lot, so I'm going to try to link up words based on some kind of co-occurrence statistic. In particular, most people settle on mutual information, and there have been at least 2 well-known attempts to try this. Basically, the Mark Paskin work in 2001 is a nice probabilistic reformulation of the Uret 98 work, trained on much more data, 40 million words of text on a Beowulf cluster for some immensely large amount of time. So this is about as good a go as you can give this task. And basically, you link up words that have high mutual information, and you do this iteratively, where you keep reparsing, collecting better statistics. Yep.
Mutual information is the notion of co-occurring in a sentence.
I could say a little bit more about that at the end, and I actually have a slide about this. Think of it as point-wise mutual information. So link them up based on something like the probability of their co-occurrence divided by...
Yeah, the question is, what's the event space?
This is point-wise over an event space of pairs of words occurring.
Okay.
Right, and right,
In the same sense.
in the same sense, right? So this is where it's a little bit, that's what happens here. Once you do iterative re-estimation, it's not actually like that because it's confined to your previous parse's expectations. I can talk about it later. I will try to argue to you in the next 20 seconds why you shouldn't really. Okay, how do you know when you're doing well? One thing you can do is you can find a gold standard of assertions that marks up what words link up to what other words. There are some issues with this too, we'll talk about later. All right, so I have a method, I have an evaluation, and it seems reasonable, right? It seems like basically the first thing to try. The Mark Paskin results, which are on a corpus I can actually go check other things against. His system with all this computation and all this data, far more than a child will be exposed to, learns about 39.7% of the dependencies correct. You say, is this good? Well, your gut reaction is that 40% is probably not too good, but the kind of the nail in the coffin is you do better if you choose to hook them up at random, right? So it's kind of worrying that choosing a random dependency structure is actually working better than this very complicated approach. But if you think about this, something's clearly going on, right? You have somebody very smart trying something very reasonable, and it works worse than random. something's going on, and it's maybe important to know what. And what's going on here is his system is most definitely learning interesting structure. It's just not syntactic structure. So here's an example. You get Congress passed the amended bill. The words with high mutual information, which however you do this will be linked up, are Congress and bill. Right? This is a topical thematic relation here. Here's a sentence out of the tree bank. Expect brushbacks but no beanballs. I actually didn't know what brushbacks were. Shows you what I know about sports, but the system didn't either. These are both singletons. They only occur together and they get linked up, as if one were the argument and the other were the verb. Right? What it's really doing is linking up things that occur together a lot. And the real killer that will show up later is a new year begins in New York. Well, the system is right. When you see new and you see New York, they do go together. But only the first one. So this is also a failing in this model that we'll talk about in a little bit. Okay, so what we've seen is that you build the system, it does detect information, it just detects the wrong patterns. Learning to link up basically nouns that are on roughly the same topic. Okay, so how can we fix this? Well, maybe individual words like Congress are kind of too laden with their semantic import. So I can imagine doing the same thing over syntactic classes like noun and adverb that hopefully have been bleached of their semantic import. So if I do this automatically and I don't actually know what the parts of speech are, the classes of words I'll get are more like days of the week will be one class, person names will be another. But basically we could build up the same kind of dependency model, which I haven't given you formally, but I can talk about later, is the same thing I did over here where I link things up based on their mutual information, which I can alternately phrase as a generative model over the whole sentence. Instead of doing it over words, I do it over parts of speech. Okay, I try that. How does that work? Well, it works better than random, right? There's some progress. Basically, we're now detecting more like the right pattern. It works a little better, but not necessarily great yet. Okay, what's the problem with this? The problem with this approach is if I wanted to do no work at all, I could just link every word up to the word before it. That's certainly easy, right? That doesn't take a whole lot of computation, and it works better. So far we're not doing all that well. This actually encapsulates some knowledge of language, namely that things are connected together locally. But somehow we feel like if we can't beat that, we probably shouldn't be bragging about it. All right, so what are the issues? The models I've presented so far, or rather that I've alluded to so far, are really too simple. They don't work much better when they're supervised. And one key thing that they're missing, if you'll think back to that New York example, the model is capable of learning that York connects to new, but it wasn't capable of learning that that only happens once, right? So one thing that I can't learn, even if I do that in the Carolyn Charniak sense, even if I learn a dependency model over parts of speech, one thing I can't learn is if I learn that nouns connect to verbs like this, if nouns connect to verbs, I'm going to connect all my nouns to the verb. Whereas the actual generalization I'd like to learn, I may or may not learn it, but the thing I'd like my grammar to be able to represent, and then I hope I learn it correctly, is I'd like to be able to represent the fact that one noun links to the verb, this noun, being a second noun, has to go somewhere else, and that'll put pressure on it to link into the first noun. Okay, so there's this problem that there's no notion of valence or number of arguments. Okay, so where are we at? We started out trying to link up heads in their arguments, pairs of words, and if you formalize this out as a generative probability model, you end up multiplying lots of factors of given a head, choose the identity of an argument, right? And this is what will give rise to the mutual information terms if you divide by p of n. So here this is kind of where you're starting with the Paskin work. If you go to the Carolyn Charniak 92 work, which works a little better, remember, we're doing the same thing except we're putting models over classes of words. Now you may wonder about this retrograde motion, maybe there's something in 82 or whatever that works even better. This is actually something that Carolyn Charniak tried, and they did a bunch of things that made it work even worse than it should have. If you re-implement it and clean up some irrelevant details, it works better than the Paskin work. But what I really want is some notion of distance. I would like to have in my model terms where I choose what kind of argument I take, condition not only the class of the head, but also on the distance. Okay, that seems reasonable, and I can do that explicitly. I can add distance into my model, and there are details on how you do it, but what's important is that you are adding distance into your model. And then you say, how does that work compared to adjacent words? Okay, so what I'm doing here, to be clear, is I'm starting with sequences of word classes, so I can compare it against the Carolyn Charniak work. From here on out, everything's going to be using sequence of word classes, which we can learn automatically or take gold classes. And this is just the comparison of what happens when you add in a distance parameter into your model, which we get a distance model with valence, abbreviates unfortunately to DMV. Here's adjacent words. This is better, if you remember, than adjacent words from a few slides back. I'm going to change corpora a couple times so that because comparing to different people requires testing on different corpora, adjacent words hasn't become any better. It's just this is an easier corpus. Okay, if you go to adjacent words and you run this dependency model with valence, it's 62.7%. Okay, and you say, is that good? Well, it's starting to seem better. We're breaking this baseline, but now really, we're above baseline, which is some progress. But you can ask this question, what's left? What are we doing wrong? And I can answer what are we doing wrong by looking at errors. So concretely, what this chart is showing is pairs of words. This is one kind of dependency where a proper noun is dependent on another proper noun, right? And these are the ones that I've overproposed. So I very often propose that a noun is dependent on a determiner, as opposed to in the standard case where a determiner is dependent on the noun. Now you might think this is silly. This is a detail of how I choose a scheme for evaluating. Okay, fine. It turns out that almost all of the top errors are a consequence of this error, and there's really only one killer, right? It turns out the system is very confused about how prepositions work. It thinks that a preposition, if I say the man on the moon, it thinks on is like a verb relating a subject and an object. But beyond that, most of the top errors actually are something else. This could lead you to wonder whether we're doing the right thing in evaluating. But the story so far, unstructured text comes in. Actually, for these latter results, sequences of parts of speech or word classes come in. We put out some pairs of words out. All the previous results were below the baselines. And we added a couple models. We added a couple features, word classes, distance. These are things that other people have thought to use for supervised parsing. And it turns out that what you get out when you train it in an iterative fashion using EM works much better than previous approaches. But we can do better later. I'm not going to argue to you that 62% is cause to jump up and down for joy. Okay. Now I'm going to talk about a different kind of syntax. And we'll go back to the dependencies later. The different kind of syntax, which many of you may be more familiar with, is phrase structure, where I basically diagram my sentence. I decompose it into a tree where there are nested components that are, in the supervised case at least, they're labeled. So the whole thing is a sentence, but also Shaw Publishing is some kind of unit. It's a noun phrase in this case. 30% of American City is some kind of unit. It's a noun phrase. Why do I want this kind of stuff? Well, the advantage to constituency structure is that I know what the boundaries of the bits of interest in my sentence are. So this means if I want to do information extraction, and I know that the thing being acquired is something over here around American City, right? I don't want to say that 30% has been acquired. That's not really complete. I don't want to say American City has been acquired because that's false. I want to get the boundaries right and say 30% of American City. These kinds of phrase structures are also useful if you want to do translation. But as I know from talking to some of you here, I have to do a little more work to convince you on the utility of these analyses as they come out. Okay, so what I'm going to try to do is model structures like this that are these nested tree structures. Now, in the supervised case, you might take one look at this and say, that looks an awful lot like the output of a context-free grammar. And I can model in the supervised case. I can model language, I can model syntactic structure as a context-free grammar, where I say there are a bunch of rewrite rules, like this one. And the local trees in my parses correspond to rewrite rules. So I have evidence now that I have some rule that says S rewrites as noun phrase, verb, noun phrase, prepositional phrase. There are a bunch of other rewrite rules in my grammar too. And I can make this statistical by assigning probabilities to those rewrites. Right? What this says is when I have a symbol S, it rewrites with noun phrase, verb, noun phrase, prepositional phrase with probability 0.1, which is almost certainly too high. Then what do? I look at a bunch of possible parses for my sentence, and I prefer the one where the product of the probabilities is highest. Basically, the correct parse is going to be the one that uses common rules most often. Okay, so that works in the supervised case, and this is actually the foundation of how supervised parsing works. And so you could think, great, I know I have a family of models, the probabilistic context-free grammars. These are statistical models, and I can do exactly what I described earlier. I can come up with a generic set of them. So I can come up with a set of grammars that have some number of symbols n, and that have rules, rewrite rules that involve those symbols. So I can take all of the rewrite rules, one symbol goes to another symbol with another symbol. So this can let me learn things like sentence goes to noun phrase, verb phrase, or anything I like. Prepositional phrase goes to preposition, noun phrase. This is there's no lots of generality here. I can represent any context-free grammar, including the ones that I know work well in the supervised case. Right? So I've got my right language family. I can do my iterative re-estimation. Right? I can do a random parse using this grammar. I can take my counts off, assuming the trees are correct. I can reparse, and I can hope this converges to some reasonable grammar. Experiments like this go back to at least Larry and Young 1990, where they tried this on some toy cases and were able to recover the grammar. But basically their conclusion is it doesn't work really well, and they're not sure it's going to work for natural language text. So people tried it later on natural language text, and it still didn't work. And the basic reason is you have in mind that you're going to get something like sentence goes to noun phrase, verb phrase, but it could be that you're going to group together your subject and your verb. Right? These are both options, and they both lead to grammars that are probably going to be locally optimal. It's hard to tell them apart. And moreover, what you're hoping to do is to learn a grammar that connects together a bunch of things you have no idea about in the correct way. You have no idea about a noun phrase or a verb phrase or a sentence, but you want to propose them all and connect them up right. That's a very hard task. Why is that hard? There's a lot of reasons, and one that I can illustrate very easily graphically that's a general problem with unsupervised models has to do with symmetries in the model. I'm going to sketch this quickly. I'm then going to present a model that does work, that avoids some of these symmetry problems, and then talk about the combinations, some data analysis, and conclude. Right, so here's the symmetry problem. I'm going to illustrate this by analogy to k-means, which is a two-dimensional clustering algorithm. Well, the clustering algorithm, I'm going to give you a two-dimensional illustration of it. So here the black points are data points in my space. They're distributed somewhere in space. And the centers, I'm going to have centers to my clusters that are in red and blue here. So what I can do is I can start both of those centers off in the middle of the space, and I'm going to do something iterative. I'm going to alternately assign all points to their closest center, and then move the centers to reflect the points assigned to them. So what I'd like to have happen is one of these to snap into the center here and one to snap into the center there. The problem is I look at something, if I start both of my centers in exactly dead center, all the points are equidistant from both centers, right? So where are they going to go when I update, when I recenter the means here? Well, the means are going to stay put. This is like a pin on its head. Right? This is an unstable equilibrium. And the way I can fix this is by injecting some noise. Any noise will do in this case. Well, except for the noise that pushes it exactly along a certain dividing line. But basically, if I have any noise at all, this is going to divide my space into two pieces. I can then assign all the points in one half to the blue, the other half to the red. And now that I look at it, the blue outnumbers the red. Okay, and that was a political joke, by the way. And so I can snap the centers to the centers to the points that are assigned to them. I update my space, and I learn something. The key thing was there was a little bit of noise to get the process started, but it should scare you a little bit, the idea that you have to depend on noise, and there's another way. Right? The problem was symmetric. There was nothing to distinguish the red from the blue here, except for this noise at the beginning. But what if I did something else? What if I had some mechanism, which you can't see because we've lost about 20 pixels here, but there's a blue circle right here. What if I have some mechanism by which I have two centers? They are starting out the same. They start out in the center, but there's a special property that this point must be red and this point over here must be blue. That's enough to break the symmetry. It's enough to give a kind of a definition of what red means and what blue means here. So they're not starting off in a completely equivalent way. Now, even if all the other points come out as a tie, symmetry gets broken by this interaction between my data and my clusters. So what does this have to do with trees? Well, there's probably two classes of people, yes?
Sorry, do you want to keep those fixed labels at later iterations or just for the first iteration?
I could do it either way, but if you know they're right, you'd like to keep them around.
If you know they're right.
So, yeah,
what I wasn't sure is whether they were just supposed to be guesses to get things started.
All right, so those are concrete questions on this specific k-means case, how I maintain, whether that symmetry is at the beginning or whether it's maintained throughout. And I mean this at a more metaphorical level. Explicitly, who knows which way will work better. In the case of trees, probably about half of you know the inside algorithm, and half of you I can't sketch it fast enough. And so let me just say broadly that what you're doing when you try to learn a context-free grammar is, over, let's say your sequences are noun, verb, adjective, noun, and you're hoping to get sentences and noun phrases and verb phrases, is you have the symbols in your grammar, x1 through xn. You have them, and you're basically trying to assign them to spans of your sentence. So you're saying, okay, noun and verb, what can go here? An x1? Sure. An x2? Sure. You go to the last three. Can you be an x1? Sure. At the beginning, all of the symbols are the same, right? There's nothing to distinguish them unless you inject some noise into the system, right? So here's a case with the Larry and Young experiments where you're relying on basically noise to get you started, and you go in whichever direction the noise suggests. That turns out to work badly for highly structured models. But the reason dependency models basically broadly work, right? The reason you get a little bit over random is because dependency models, although I haven't shown you this, dependency models are roughly context-free grammars where the symbols in your grammar match up one-to-one with symbols in your yield space here. So it's as if I have one symbol for noun phrases, one symbol for verb phrases, one symbol for adjective phrases. Now there's going to be a structural requirement if I set my grammar up that I can say that over a sequence noun and verb, these two categories can be built because they appear in the span. I can say the same thing over here with noun, verbs, and adjectives. So now dependency grammars are essentially context-free grammars, except they all have this special property that all of the symbols in your grammar, their meanings have been predefined to relate to your output. Okay? And this is very powerful, right? It means you don't need noise to break your symmetries. You've already said what all the symbols mean, how they're all different by how they anchor into the output. Okay? So that's a way around model symmetry where each symbol has its own predefined meaning that happens to be what makes dependency models basically work. Although I haven't shown you that they work stunningly, they work at all. Okay, there are other approaches. Lots of people have worked on this. How do we know who's doing well? We can pretend it's like the supervised parsing task. We generate some trees and they're right or they're wrong. But it's a little tricky because the labels of the nodes don't necessarily mean anything. I say it's an x43, but you say it's an x28, and the right answer is noun phrase. Who knows who's right? So one thing I can do is I can look at the assertions in my correct tree. My correct tree may say words 7 through 12 are a noun phrase. I can ignore the label, and I can check to see how many of those brackets I get right. So if I have something between position 7 and position 13, I get it right. Okay, obviously, there are some freebies. Right? Every tree that you pick is going to have a node or a constituent over the entire sentence. Right? So I can look at what would be unlabeled recall. And for the rest of this, there are going to be a couple corpora. I'll point them out as I go. Basically, here I'm just going to give you the unlabeled recall. This is one of the higher numbers I could give you because there's no upper bound to it. But if people want to see F1 or precision, I have those later, and I'm happy to show you. Here's some recent work. And actually all very interesting stuff that I highly recommend if you're curious about this topic. Adrian's in 99 basically makes a theoretical statement, right? Which is language grammars aren't general context-free grammars. They're a certain kind that obey a certain kind of learning condition. And then you can basically turn this into a special learning algorithm. Here you get about 16% of the brackets put in the right place. Okay, so you think maybe that's not great. Alex Clark basically builds filters where you try to detect constituents using mutual information criteria, and then you try to assemble them with some kind of heuristic search, minimum description length. This gets you about 34%, doing about twice as well. Menno van Zanen, this I actually think, kind of pre-theoretically, this is probably the most appealing thing to try first. This seems like a great thing to try first, because it seems like the kind of thing that a linguist might argue for. You find pairs of sentences that are nearly the same. Like, I would like a flight to Denver, and I would like a flight to New York City. You look at where they're different, and you say, where they're different, that's a constituent. Denver is a constituent, and New York City is a constituent because there seems to be some kind of substitutability there. Okay? That seems like it makes sense. You get about a third of the answers right. Now the problem is that if I wanted to do very, very little work in parsing sentences, and I didn't care what the labels were on the tree, I could just take your sentence and give it what's known as the right branching structure that looks like this. Okay? In this case, the right branching structure is perfect. They were unwilling to agree to new terms. Every suffix here is a constituent. All right, so this is easy. It's certainly a lot easier than any of these three things are to implement, right? And it's English specific, right? Other languages may not work that way. But you take the best of the previous crop, the Van Zanen work, right branching structure works better. This is on the ATIS set, which is actually about, right branching usually works even better than this. It's particularly bad on that. Okay. So now we're in this position where we've seen a bunch of different kinds of models of different kinds. Basically, these are different kinds of either probabilistic or semi-probabilistic models. Somebody phrases an interesting model. It learns something, but it usually learns the wrong thing. It detects some other kind of pattern, or there's some kind of structural complexity in the model that prevents it from learning the right pattern. What we want to do is we want to build a model that is going to kind of be good in two ways, right? We want the right answer to somehow be unavoidable in this model. That's probably not going to happen, but we'd like to facilitate learning. So the kinds of things that seem to have worked so far that we could use as desiderata is it seemed like using word classes for a variety of reasons works better, at least to get you started, than specific words. Because there's lots of specific words, and it's easy to detect semantic patterns when you have words in the mix. That's one thing you might worry about. You'd like, if there are symbols in your grammar, class 1, class 2, class 3, you'd like to have some kind of property that makes those classes not equivalent. Otherwise, you have to inject noise, and injecting noise is always scary. If it doesn't scare you, it should scare you. And then I kind of alluded earlier that you might get yourself into trouble if you're hoping to learn a grammar, like a probabilistic context-free grammar, where your whole knowledge about language is encapsulated in relationships between a bunch of symbols that you know nothing about. That's going to be dangerous, because you're hoping to learn stuff that you have no direct evidence for at all, and that's pretty subtle. All right, so let me tell you about something that does work extremely well and robustly, where this is reasonably extremely well. Right? Extremely well in the space of unsupervised methods, which tend to be much less well correlated with the correct answers. Let's say what we want to do is learn word classes. Up till now I've been saying, I assume word classes, but I didn't tell you where the word classes come from. Here's a great way that you can try yourself at home for making word classes. And what I mean something by you can try yourself at home. Basically, whatever you try along these lines is going to kind of work. Right? This is reasonably robust as far as these things go. You take a sentence, like the president said that the downturn was over. You take each word, like president, and you count up what environments it appears in. So here president is occurring in the environment between the word the and said. Or maybe the environment is after the, and then secondly you count up before said. So you collect a bunch of counts that represent the environments where each word occurs in. So president occurs here, governor and some larger corpus may occur in the same environment once, a similar environment, and you do this for every word, and then you cluster words based on whatever notion of clustering you like, such that words with similar counts of signatures here, words with similar environments get put together. You can formalize this in a million ways. Here's at least two good early examples of this. People have elaborated this in many ways. And basically, you can do better or worse, but you're going to detect clusters that kind of correspond to some mix of syntactic and semantic classes. So reasonably, you might expect to put your determiners together, some communication verbs together, but not all verbs, some kind of title words, but not all nouns. These are the kinds of patterns you'll learn. Now, why does this work? You might think it's amazing that it works, because now you could stop me and you could say, all right, I'm tired of you alluding to models. Give me a probabilistic model so that I can think about this as a probabilistic model. Well, the closest I can do for you for this kind of word clustering that I alluded to is I could say, imagine the following. And if there are two kinds of people in the room now. There are people who are already in pain from this expression, and there are people who I'm going to have to kind of point to why you should be in pain. All right, here's the situation. My generative model, where I tell a story about how my data came into being, this involves going position by position, independently deciding a class for this position. So C1. I hope C1 turns out to be determiners, but whatever it is. Some class C1 to this first position. Conditions, that's this. I choose a class. Then, conditioned on that class, I generate my word, right? And so maybe it's a determiner word like the. And then, dependent on my class, I independently generate its context, either jointly or I can factor that as well. All right, this is a generative model, and it would be reasonable if I had pairs of words. So I do this at each position. I do this at each position. Each position, I choose a class, I generate a word, and I generate left and right. Now, what's the problem with this? The problem is one word's left neighbor is another word's right neighbor. I'm basically generating the sentence 3 times, right? Because this word gets generated both here and here and here. But this is basically what you're doing in the distributional clustering, and it basically works. Compare this to what if I stuck you in a room with a probabilist and I said, give me a model where there's a symbol at each point. The obvious thing is a hidden Markov model, right? In a hidden Markov model, I generate each class conditioned on the previous class, and in a given position, I generate the word. Much cleaner. Backed up of years and years of mathematics. And we have really good inference algorithms for this, the Baum-Welch algorithm. And you can do it. You can learn up classes for words in this way. Now, this is kind of ugly. It's over-generating. And it somehow feels wrong that we're not linking up the classes, because classes should relate to classes. Now, that's one difference. This is prettier. The other difference is that this one works, and this one doesn't, when you try to learn word classes. Now, you should always be worried when one thing works and something that feels like it should be better works worse. And it's disastrous if you try to learn word classes like this. And there's a really good reason for it. The reason for it is here you've said, I'm giving you a Markov process. And conditioned on that hidden state, you have to predict the words. Right? But I haven't told you what the process looks like. Right? I haven't told you that there's supposed to be nouns and determiners. And I haven't even told you that each word is supposed to be a different part of speech than its neighbors. That's actually not even true. You can have sequences of the same part of speech. But what you get is you get the ability to encode things like C17 is the state that says omit all words in all capitals. It'll be a headline state. I might have another state that likes to omit numbers, or a state that likes to omit semicolons, or something else that is information across the entire sentence. This hidden sequence is capable of correlating the whole sentence because the whole sentence may be statistically correlated. And you learn those patterns. So you get, how come this word is a member of so many different parts of speech? They're not parts of speech. They're states of the sentence's grammatical distribution that you can be in at that point. Here, every word is isolated. I've broken the links. It's made a little bit of a probabilistic mess, but by breaking the links, I ensure that whatever pattern I learn is localized to the words. And then it turns out I learned something about what I wanted to learn, because what I wanted was a relatively obvious pattern that's localized to the words. And if I don't force that, it's not going to happen. Okay, so we've seen distributional models that basically work and detect the structure, and then a kind of a high-level correlation between them that we want to break. We don't want them all linked, all the hidden symbols linked up to all the other hidden symbols. We can say the exact same thing for grammar, right? I can say, I'm going to take out sequences like fell in September, and it's going to have some context. Except remember, when I do this, I've already got word classes, so the context is noun to end of sentence, right? So I take out all of the subsequences, and they all occur in certain contexts. I take counts off of a corpus, and I start clustering. All right, what do you get out? You get what you might think. You get things, and again, these are examples of them, but these are, I put in specific words for concreteness. You get things like the final vote or 2 decades or most people. That's a good class. All these things are constituents. They're all noun phrases. That's good. They're constituents of the same type. So are these. These are all prepositions, or prepositional phrases of the same type. But what about this, right? Whatever they are, they're of the same type, right? They're kind of preposition determiner. Okay, I don't want them in my trees, but they are, you know, they're bad in exactly the same way. So now what I have to do is I have to go through and say, I like those, I don't like those. You can make this work. This is the Alex Clark approach. And as far as I know, it's kind of the runner-up broad coverage to what I'm arguing here in terms of numbers. You can make this work. But see, the problem is, if I look at various sequences and I ask you to label them, I say, here are constituents, tell them apart. This is in 2 principal components, noun phrases, verb phrases, prepositional phrases. They're pretty distinct. Right? Noun phrases distributions really are very different from verb phrase distributions. You know, one is the beginning of the sentence, the other's in the middle of the sentence. You can tell them apart. But if I ask you based on context to make a 2-way decision, good versus bad, like it belongs in my trees versus it doesn't, this is a weird question to ask. And it fails in 2 principal components. It kind of doesn't look promising. This doesn't prove that it's not going to work with a couple more components. But this is a hard decision. Right? There's nothing that uniquely specifies good stuff versus bad stuff. Right? So this approach may not work. But we'd still like to have some model that does this basic distributional thing of tying nodes to their context so that everything's grounded and not correlated, that the symbols aren't all connected to each other. And we'd also like to have some model that gives us tree structures, that doesn't ask some post-processing system to pick the good from the bad. Because a good hypothesis is kind of a hypothesis that fits with the other good hypothesis. It's not something you can decide in isolation. And we'd also like our symmetry, the model to have no symmetries. Here is such a model. I'm going to spell out the probabilities for you, or at least the important term, but I'm going to do it very rapidly. So questions if this isn't clear. The basic process is we're going to generate a tree structure according to some distribution over tree structures. It's uniform of some kind. let's say. And then we're going to populate our sentence conditioned on the tree structure. We're going to do it in the following way. We're going to overgenerate it massively. It's going to look like this. We're going to go to every node in our tree. So let's say for this sentence, factory payrolls fell in September, I choose the correct tree. What's the correct tree look like? The whole thing is a sentence. There's a noun phrase here, there's a verb phrase here. Okay. I will also do this for all the incorrect trees. I will do this for every tree, and then I'll take counts and I'll re-estimate. Okay, but for the correct tree, the generation will look like this. I know I have a constituent. There's going to be two classes, plus and minus. For a constituent, I then choose a filler. Any constituent filler. Hopefully I choose noun, plural noun, verb, whatever. That's what I have to do to get this sentence. Okay, so as a constituent, I choose a filler, and then I choose the context. I choose them independently. I do this for every node in the tree. So I go to this node, and in order to get this tree, I have to choose a filler, and it actually has to be the same filler as before, but we're going to ignore that. I'm going to choose a filler for the noun phrase, I'm going to choose a filler for the verb phrase, and so on. I'm going to go to every node in the tree, I'm going to generate a constituent, not even conditioned on type, and a context. I'm actually then going to go and do this for every node that isn't in the tree, except now I'm going to condition on another symbol. I'm going to condition on minus. So what have I done here? I've basically said I'm going to generate every span, right? There's going to be quadratically many of them. Every span of the sentence and its context, conditioned on some symbol, plus or minus, where plus and minus where the difference between plus and minus is essentially the pluses all nest nicely like a tree does, and the minus is kind of anti-nest. So I've got two classes. It's just like distributional clustering with two classes where, remember I said there had to be some kind of way to break the symmetry to make this problem possible? It's two classes where the definitions of the classes are pluses nest, minuses don't. And I iterate. Okay, how does this work? Well, here's right branching structure. This is on short sentences. This is word sentences that are 10 words after you take all the punctuation out. There's a lot of them, but they're short. So right branching, it turns out, with Newswire works fantastically well, 70%. This model, the constituent context model, works about 81.6%. And so you ask yourself, I mean, if you're not used to staring at parsing code, you say, I have no idea what that means. Is 81.6 good? Right? It sounds better than 41 from earlier in the talk, but what is this? What does this look like? Right? This is about the kind of output you get at 81.6. Here's the tree bank parse. There's a sentence, a noun phrase, a verb phrase. The screen was a sea of red. There's a prepositional phrase here modifying this noun phrase. And this system outputs this, right? There aren't categories, right? Because there's only plus and minus. These are the symbols that were plus. I can name them anything I like. I have a constituent over the whole sentence. That's right. And I have this noun phrase and prepositional phrase, and they're linked together. But I've made a mistake against the gold standard. And that is I've lumped the verb with the subject rather than with the object. Okay. Other than that, this tree is right, but there's kind of a big mistake right in the middle of it. That's about what 81.6 means, as best as I can give it to you in a single tree. All right, I can look at the errors, and I can ask questions like, what's wrong? Is it my system, or is it the gold standard? And, well, to be honest, usually it's the system, right? But that's not always the case. So the system likes to analyze the internal structure of noun phrases. It turns out the tree bank doesn't analyze them. For possessives, if I have John apostrophe S cat, what's the right bracketing? Is John apostrophe S a constituent? Well, that's kind of what the way we spell it would indicate, and that's what the tree bank says. But this system likes to kind of treat this apostrophe S as a determiner. Linguists have certainly argued for this, but there's no question that this is defensible. And then on the probably entirely wrong side of the spectrum, this model is working about 80%. It likes to group modals with verbs. Yeah, it's probably not right. It doesn't really reflect where we can stick adverbs and that kind of thing, or what we can prepose. But it's not totally in left field, but it's wrong. The worst errors aren't these ones. The worst errors are kind of the weird, strange things that happen where one sentence pops out and it's just complete salad and you don't know what to make of it. Okay, so let's talk about where we are so far. I've now gone through, again, a second model where unparsed text comes in. Actually, it comes in with word classes, not words. And I start pumping out trees. Rather than giving you pairs of words for you to evaluate, I'm now giving you tree structures where the labels are erased. They're not part of the evaluation. Right, you can go back and label them later if you like. So text comes in, kind of nested span trees comes out. And they're either more or less right. So the new idea is here. We took the distributional clustering, which as far as I know is the most robust thing out there for language learning. Lots of different formulations. They all basically work, even if you make a couple of mistakes along the way. We built some model which had issues that derive from one thing that actually is very beneficial for this model. This is a model that has nested structures, but does not relate those structures to each other recursively. Right? As soon as you do that, you end up with a problem of multiple generation. But it's what made distributional clustering work, and it seems to be what's making this model work as well. Then we use some structural bias to kind of tell the pluses from the minuses. One of them nested, one of them didn't. And what we have now is basically two models of syntactic structure. Each of these is the first to break its baseline, and you'd love to be able to kind of put them in a pot and cook it for a little bit and get out something that works even better. And you can. In general, there are lots of ways you can combine multiple models, and I will do my kind of quick poster for another paper that I'm not going to go into here. But you have this general case where you've kind of got some purple thing, and you're going to split it into red and... This is actually seeming very timely. You're going to split it into red and blue, and you have some function, one that comes from one model, one that comes from another model, and you'd like to, if nothing else, find a structure that simultaneously makes both of the evaluations large. So you maybe learn them separately, you learn them jointly. You want to do some kind of combination. I think I don't have time, if I want to end on time, to go into the multiple cases of this, but the basic idea is you come up with a structure, a label dependency structure, a lexicalized phrase structure tree that kind of encodes both dependency and constituency. You now can project it to either kind of structure, model them separately, and then combine them. So what happens when you do that? I'm happy to answer questions on how you do that, but for now, assume you're matching them together in the simplest possible way, pointwise multiplication over the structures. The answer is, well, remember we had dependency evaluation before, and on these 10-word sentences, choosing a random structure links about half of them up correctly. The DMV, we got excited at the time that it broke the baseline, and you do your model combination, and well, it's not really convincing, right? It's about 2% better, that could be noise. It turns out that if you look at these errors, they are better, but you shouldn't take my word for that. You should either look at the data yourself or not believe me. But in the constituency evaluation, we seem to have accomplished something. The CCM is about 81%, and the combination of models is about 88%. These are short sentences, and a supervised parser would do better. A state-of-the-art supervised parser would certainly do better, yeah.
So if I understand right, the reason the constituency evaluation is looking better here is because you're guessing the heads differently from your gold standard.
No, that's right. So largely the difference is here we have a huge systematic disagreement with the gold standard.
Sure, about whether determiners modify nouns or vice versa.
Yeah. And here we don't, right? So, you know, there are issues with evaluation. And I mean, I can't tell you anything other than we honestly do not know how to evaluate these systems in a perfect fashion. I would argue to you that probably there's a little luck here. What?
You can just assume the DP hypothesis and declare victory.
Yeah, but then I get yelled at for choosing my linguistic theory based on what my system does, which, while that might actually be a data-driven way to do linguistics, maybe it's hypocritical for me to do it. You can declare the DP hypothesis, and you and Steve can declare my victory formula if he still believes it. Okay, so we've done better. I should say you can do much better if you build supervised, and this should not be a surprise. But there's qualitative improvements. So those subject-verb groups I showed you, they're gone. Modifier replacement improves. If you look at these trees, you think, wow, you can look at these trees, and if you look at them with the right mindset, you think, that looks like the output of a kind of mediocre to bad supervised parser, right? That's actually great, right? The fact that I have to get up to you and defend that exactly where we are with respect to supervised parsers, as opposed to saying, we broke random, but not the baseline, right? This is actually where the progress is. This is not solved, but this is, I think, a large amount of progress. How general is this? You run it on English and you think, well, you can parse at reasonable accuracy the only language we do not need grammar induction for. Okay, so fair criticism. German, you take about 2,000 sentences. Similarly, they're short sentences. The random baseline is actually a little larger for interesting reasons because of how German's structure is different. But you actually, by the numbers, do better. Although really, in terms of error reduction, you're doing worse. But you're broadly capturing German. Well, that's good news. Chinese, not so great. Now, the baseline is lower, it's a lot lower, and supervised parsers tend to have about double error rate. So if you go by that heuristic, that a supervised parser gets double error rate, no, we're probably still doing badly, but what's interesting about this is we're getting the dependencies just about as accurate as in English. Moreover, this kind of bad performance at constituency doesn't change the fact that when you add the constituency model to the dependency model, it improves substantially. So I honestly don't know what to make of the fact that this is lower, but it does seem like the model is capturing enough to at least improve your dependency scores. Take from that what you will. All right, so what's been accomplished here? I tried to present two kinds of structure. This looks more like the supervised number than the baseline, and that makes me happy. And why does this work? We're combining two simple models. We're using representations that were kind of designed by looking at other models, previous attempts, not saying, oh, that didn't work, but saying, what is this learning that it shouldn't, and how do I change my model so that that information is unavailable, word classes, or by constraining how recursion is done, whatever it's going to be. This is cool because provided you can get this unsupervised stuff high enough to be useful, you can do this to do that, right? You can start basically bootstrap tree banks where you guess with an unsupervised model and maybe somebody cleans them up. You can imagine directly applying this. This produces trees. What do we use trees for? We usually take features off them and stuff them somewhere else. Like maybe your named entity recognizer likes to know where the constituent boundaries are. We can use these trees instead. You could try to learn other notions of syntax. You could try to learn syntax for translation. Now I'm speculating wildly. This isn't something I've done. And you can imagine cases where the tree bank's just not going to be available. Yeah, again, larger crowds laugh at that. So thank you very much. I have tons more slides if you have questions, but I'll end here because this is where I...
So I think it's a measure of the clarity of that talk that you got through it with almost no heckling. That's very unusual around here.
It's not just because I talk extremely fast and shake my arms a lot.
You might be intimidating us, that's possible.
Great.
You haven't talked about the amount of data. I mean, the whole point about unsupervised work is that you can take advantage of this amount of data. There was nothing.
I said, and you'll notice it's missing from my my motivation too. So that was very tactical. You're totally right. I said two things that were in direct contradiction. The first thing I said was, kind of, there's all this data, we want to harness it because training sets are expensive to create. And then I went and said, basically to get these good state-of-the-art results, you need like 7,000 sentences, less in German, right? Which one did I mean? I kind of mean both. So the reality is, in order to learn structure, basically, to learn it well, you need to have a highly constrained model, and for a highly constrained model, a small amount of data will do. I mean, you need your model to detect that nouns go with determiners, and determiners do not go with prepositions. If you can get these basic facts down, you're going to end up in basically the right point in space, and you don't need that much data to establish that. So what you have is you have a situation where to learn the basic broad structure, you want a simple model that doesn't require much data. Now what you want to do, and I haven't done, and I haven't even sketched a way you might do this, but you could imagine one, is now saying, okay, we've basically gotten to, something that looks like English, it's just not very good at parsing. And now you want to start allowing in something like lexical probabilities or a richer model that can take advantage of a larger data. So I think you want to phase in your parameters and complexity so that you can exploit larger and larger sets. That's a completely open area.
And you haven't tried this with more data. I mean, there is no learning curve. And then if you have 1,000 times more data, does it work better?
There is a learning curve, and the data points the other direction. If I use 10% as much data, it works nearly as well. Right? So I have reason to believe this is leveled off, which is what you'd expect. If you actually look at the number of parameters, this is an extremely simple model, and that's important, right? It's the right simple model, or well, no, that's too strong. It is a surprisingly good simple model, and not much. You kind of get to data saturation. All the parameters that you really need are these small chunks. They drive the rest of it, and you have data for them. So in some sense, one thing I can do is I can train the supervised, and it doesn't actually work much better. So this is a model that is not designed for high accuracy parsing. This is a model that's designed for quickly learning the broad structure so that you kind of get the right broad structure. You would have to do something more in order to exploit large amounts of data.
So it does look like CCM is efficient, is that right?
It is more deficient than any model you have ever called deficient before. I mean, I don't know the technical term. Massively, horrendously deficient, sickeningly deficient. Yeah, it's very deficient.
So is it advantageous or is it something that's problematic?
If I knew a way, so the key thing that I have in my head when I think about these is you need a model that does not require you to postulate too much interesting about hidden categories. Dependency models do that by predefining the symbols. This does it by decoupling them all in the way distributional clustering does. The dependency model feels better. The consistency model works better. In the same way, I would love to be able to find some way to trick an HMM into learning the structure I want. I would love to not have to do distributional clustering. Similarly, I'd rather do this all with something like a dependency model. And my guess is that there are ways to do that. And I have some preliminary results that I'm not ready to say anything about that suggest there are ways to clean this up. It is a flaw in the model, but it does stem from a completely intentional thing, which is the decoupling. If you don't have, if all of the nodes are decoupled except for their nesting criteria, I don't see any other choice except something that would involve very expensive renormalization.
Instead of thinking of them as efficient models, can you think of them as some sort of exponential model where you're missing some sort of partition function? Because after all,
Yeah. So yeah, if I could do that normalization, I could think of this as just a big maximum entropy model.
Yeah, and then you say you're doing the approximate calculation.
Yes. It's not massively deficient. I'm doing an approximate maximum entropy model.
So there's one piece that you left out, which is very important for making these models work, which is the initialization.
Yeah. Okay.
So would you like to say anything about that? And do you have anything to suggest that that isn't as important as I think it is?
No, you're right. I mean, okay. Let me skip through some slides. Oh, we already saw this one. There's some errors. You can ask about them later. No, I put the wrong slides. They're flying by. Okay, here we go. All right. So I say I only told you how to generate a sentence given a tree. Normally, sentence given a tree is a dead boring thing, right? You read the leaves off, right? But this is actually, I choose a backbone for my tree, and I kind of fill in the details. So in this model, it is meaningful, and the interesting part in terms of number of parameters is how you generate, and specificity of the parameters, is how you generate the sentence given the tree in this previously thought to be deficient way. How do I get my trees? One option is I choose a tree at random, right? And another option, right, there's a certain number of binary trees, I pick one. Right, they all have equal weight. You can worry about whether I can do that efficiently, but I can. Another thing I could do is I could say, I'm going to start with n symbols, and I'm going to split somewhere uniformly amongst my options, and I'm going to recurse. That gives you a different distribution over trees. It turns out it's an extremely different distribution over the trees, and the way it's different is basically this. Right? In print, I can kind of do this for a bigger grid if people are interested. I have figures, but the thing to notice is this is a big empty hole, and this is kind of the same across the diagonal. And if you do this for a big grid, what you see is this distribution here disprefers chunks in the center. Turns out language disprefers chunks in the center. Not English, pretty much all of it. And so it seems like, while this, you might worry about the differences, at the end of the day, there are two relatively knowledge-free, in some sense, distributions over trees. This one gives you a set of trees that is kind of at all in the ballpark, because there are a lot of trees out there. Once you have something that has 10 or more terminals, there are a lot of trees. And if the vast majority of your trees at initialization have these kinds of center chunks like this, and they're being overgenerated, you can see this one would rather have chunks on the outside than chunks in the center. You're going to learn the wrong thing, right? And initialization is important.
Just help me interpret
Yes.
this picture. This is some sort of
This-
grayscale where this is the probability that that span is a constituent.
Yeah, this is, that's right, I should have said this. This is a kind of a standard, if you think CKY parsing, start position, stop position. It's a parsed triangle where the darkness is the posterior fraction containing. So every tree has the kind of, each word is a constituent and the whole sentence is a constituent. And they vary about where they put their constituents in the middle. So putting constituents in the center is bad. And for various reasons, if you do allow a uniform distribution over trees that does that puts mostly these kind of balanced center chunk trees, that works against you because there are so many trees, right? Language trees are this very specific subspace of the set of all binary trees, and you're better off using this kind of initialization. These things are important. The best thing I could say is I don't believe this is extremely language specific. You could think this is what's going wrong with the Chinese, that maybe this was too much like English and German, but this is worse for Chinese. And if you look at the distribution, the empirical distribution of where constituents go in the various languages, they all look like right branching, broadly. And nothing's got any chunks in the center. Was there an answer in there somewhere?
Yeah.
So something else maybe you can talk a little bit about is learning from tag words rather than learning from tags.
You mean not assuming parts of speech going in?
Parts of speech.
Okay, so the short answer is the combination model started with entirely raw text, automatic parts of speech, and then the model using those parts of speech.
Automatic parts of speech by distributional clustering.
Distributional clustering. Not good distributional clustering. What we did was, I would say we used, so I had a couple early sites. One of them was the Schutze method. I would say we did the Schutze thing, except ours was even simpler than what he called his baseline method. We kept casing information, so all words at the beginning of a sentence are in different, it's a mess. You look at these and you think, there is no hope you could ever get anything out of this. The combination model suffers by about 5%. It gains more than 5% over the CCM. So using completely automatic, the combination model is capable of outperforming the CCM with the tree bank tags. You can also learn nearly as good numbers as that, where you say my parts of speech are 50 most common words are their own part of speech and everything else is the other part of speech. So what's nice about this is it kind of doesn't matter what you do for your parts of speech, which maybe you would like because that might mean that they're somewhat independent if it's true that they both have to be learned independently.
One more question about how you evaluate the unsupervised constituents.
Mm-hmm.
You said you just use unlabeled precision because
Unlabeled recall.
unlabeled because you don't know what labels to give to these.
Yes,
things
I could do best match or something.
Yeah, or you could do something like a post-hoc best possible assignment. So if you
Yeah,
so
except I only have one label in the constituency model.
Oh,
Everything is label plus. All the other spans are labeled minus, but it's not interesting. The ones in your tree are all labeled plus. I've done this with labels, right? I mean, there's a formulation of this where the instead of just picking plus or minus, if it's plus, you then pick a label and condition on that. It works about the same because you win some specificity, but you lose the fact that lots of kind of constituents share the same context. If you do that, the labels are kind of great, right? I mean, the classes, they're mostly noun phrase labels, but there's the verb phrase ones. The labeling is easy. So I try to give these two pictures. Labeling is a dead easy task. So while I'm sure the numbers would be quite bad, in the sense that it wouldn't be a perfect matchup, and you lose something from the unlabeled scores because some of them would be in the right place but have the wrong label, right? You'd probably lose 5 or 10%, but you wouldn't. It wouldn't be devastating if you did a kind of best post hoc reconstruction with a model like that. But labeling is easy. Bracketing is very, very hard.